Welcome to the video lecture on finding limits graphically and numerically. One fundamental concept used in calculus is the idea of a limit. We are going to learn an intuitive approach today to finding a limit. We're going to do it graphically and numerically. So let's take a look at the following example. We have our function f of x, which is the quadratic function x squared minus x plus 2, and we're going to examine the behavior of f of x near x equals to 2. So one way to do that is to use a table of values, and this is called a numerical approach, where you're making a table of values. And what we're going to do is look at values of x near 2. Now that implies looking at values of x that are slightly smaller than 2, like all of these x values here, and also values of x that are just slightly bigger than 2, which are all of these x values as well. So you need to look at both sides of 2, to the left, slightly smaller, and to the right, slightly bigger. So we're going to look at what these function values would be. And to do that, you can just plug in each of these x values into your function, which can be kind of tedious, or we can use our calculator to help us out. And there's two different options for you. You can use the table feature on your calculator, or you can use lists, and I'm going to show you both options. So to do the table feature, the first thing we're going to need to do is type in our function into our y equals. So I'm going to go over here to y equals and type in x squared minus x plus 2. And then what I'm going to do is I'm going to set up my table so that it starts at an x value of 1. So I'm going to use this table set command right here. So I have to do second window, and I'm going to start my table at 1. Now this next feature down here, this change in table, tells you by how much you want your table values to go up or down by. So this would be going up and down by 1/10. So I'm going to just leave it at that for now, and I'm going to go ahead and look at my table, which is up here right above graph. So I'm going to do second graph, and what this tells me is that when x is 1, y is 2. And if I look down in my table, I can also see that when x is 1.5, y is 2.75. If I scroll down, when x is 1.9, y is 3.71. Now to get the next value, that's not going to show up in my table as it is right now. So I'm going to have to change my table set. So I'm going to go back to table set, and this time I'm going to have it start right at the value I'm interested in, which is 1.95. And since the next value in my table is changing by hundredths, I'm going to arrow down, and I'm going to change my table to go by 0.01 so that it'll go by hundredths as well. So let's go to table. 1.95 gives me an x value of 3.8525, and 1.99 is 3.9701. Now let's change our table set to start at 1.995, and let's go up by thousandths, so 0.001. So 1.995 has a y value of 3.985, and 1.999 is 3.997. And if I change my table set to the last value here, 1.9999, that's going to correspond to 3.9997. And if you were just to plug in 2, it did show it earlier in our table, but if I plug in 2, 2 squared is 4, 4 minus 2 is 2, 2 plus 2 would be 4. Okay, so doing it using tables, it's doable. It's a little bit tedious, however. So I'm going to show you a second option, which is to use lists, and I'm going to create a list for this second table that we need to figure out. So the first thing I'm going to do to create a list is I'm going to go to the stat command. So I'm going to hit stat, and I'm going to hit enter. And this is what my lists look like. Now if you have values already in your list, you're going to want to clear them out by just arrowing up to the top so that the label is highlighted. Press clear, and then hit enter, and that should clear out everything in that list. And in this first list, I'm going to type in all of these x values that I'm interested in finding values for. So let's go ahead and do that. So I want 3, hit enter, 2.5, 2.1, 2.05, 2.01, 2.005, 2.001, 2.0001. So all of these are just getting slightly smaller each time until eventually we get down to 2. Now once I have those typed in, I'm going to arrow over to the right and arrow up to the top where that L2 is highlighted. Press enter so that your cursor is flashing down here at the bottom. Now down here is where I'm going to want to type in what my function is. Now normally our function f of x is x squared minus x plus 2. But we aren't using x's so much as we're using the values that are listed here in L1. So instead of typing in my function and writing in x squared minus x plus 2, I'm going to change these x's to L1s because L1 is where we're getting our variable values from. So L1 is right up above the number 1 on your keyboard here in blue. So I'm just going to type in, instead of x squared, I'm going to type in L1 squared. And then instead of a minus x, I'm going to type in a minus L1. And then I'm going to add 2. So this should look exactly like our function's formula, but instead of x's, it has L1s instead. And if we hit enter, automatically we just get this whole list of values very quickly. So I like this technique a lot more when I have to do a numerical method because I think lists are much quicker if you have a lot of values to compute at once. If you only have a few to do, then tables is usually fine. But if you have a lot, then I just stick with lists. So let's go ahead and copy these down. So when x is 3, we got 8, and 5.75, 4.31, 4.1525, 4.0301, 4.015, 4.003, 4.0003, and finally 4. Okay, so we just created a table of values using values of x that are slightly smaller than 2 but approaching 2 as we progress down this table. And then on the other table we have values of x that are slightly bigger than 2 but still approaching 2 as we progress down the table. What is this table telling us? As these x values get closer and closer to 2, what are these y values getting closer and closer to? Well, hopefully it's fairly obvious that these y values are getting slowly closer and closer to 4, and also here slowly closer and closer to 4. This is called the limit. Okay, so when you have a value that you're looking at, namely x equals to 2, and you look at values of x getting closer and closer to it from the left and from the right, if you have y values that are also approaching a certain number, then that would be called its limit. Okay, so what we're going to say for our notation, we jump down here, is that the limit as x approaches 2 of this function f of x, or if you prefer, you can write the limit as x approaches 2 of the formula. You can either use f of x or you can use its actual formula. This limit was that y value that these tables were approaching. Okay, this is called a numerical approach when you're just using tables. We're going to approach this now graphically instead and see if we can figure out that same answer from a graphical approach. So the first thing we're going to want to do is graph it, and we already have in our y equals this function, so you could just hit graph and you could copy that graph on here, Or we've already done all the work to create a bunch of y values here, so we could just plot some of these points. When x was 1, y was 2. When x was 2, y was 4. When x was 3, y was 8. If I were to plug in 0, we would get 2 as well. And you could plug in -1 and so forth. But we know that this is a parabola, so it's going to have this shape to it. Now here's how a graphical approach works. We want to look at what happens to this graph as we approach 2. So here is 2 on the x-axis, and I want to look at values of x that are slightly smaller than x and getting closer to 2. Slightly smaller than 2 and getting closer to 2. So that would be these little x's down here. Now what y values do those x coordinates correspond to on my graph here? Well, they correspond to these dots going this way. So as my x's go to the right, my y's want to go up. Okay? Now let's look on the right side of 2. So what happens if I look at x's slightly bigger than 2? So I would be coming in this direction. Those are all x's slightly bigger than 2, and those correspond to these y values on the graph up here, and they would be coming downwards like that. So here's what I tell students to do. To figure out what this limit is, imagine that these are 2 cars driving on this function, driving along this road that is the graph of this function. You've got one car, the black one, that's driving up as we get closer to 2 from the left side, and one car, that's the one in blue, driving down this curve, down this road as we get closer to 2 from the right side. Do the cars want to crash? If the answer is yes, which it is in this case because these 2 cars want to crash right where their arrow tips want to hit each other, then we say that there is a limit. And the value of this limit is the height of where those cars want to crash. So the limit will equal to the height, in other words, the y value of where they crash. So if these 2 cars want to crash right here, that is at this height right here, which is 1, 2, 3, 4. So these 2 cars want to crash at a height of 4. So our notation that we had before, that this limit as I approach 2 of my function is equal to 4. So the y value goes here, the x value goes here. Alright, so imagine cars driving along a curve. If they want to crash into each other, wherever they would crash, whatever that height is or whatever that y value is, that is going to be the value of your limit. Now notice on this particular curve and on this particular function, if I had just taken 2 and plugged it into this function, 2 squared minus 2 plus 2 is equal to 4. And that's a nice property to have. If you can just take 2 and plug it in and get the value of your limit, that is called continuity. So the fact that we could just plug in x equals 2 to get the limit implies that this function f is what we call continuous. And we're going to talk more about continuity in a future lecture, but it's a nice property to have because it means we could avoid having to make all of these graphs and making these yucky tables up here. We could avoid all of this work and know that our answer would have just been plugging in 2 and getting 4 for an answer. So it helps us to avoid some of the messy work if our function is continuous. Let's try another example. So this time our function g is x squared minus 9 over x minus 3, and we want to look at what happens to g near x equals to 3. So to do a numerical approach, we're going to make tables again. And remember that when you're doing this on your own for your homework, you want to make sure that you're making tables where the x values are values of x slightly smaller than 3, which would be all of these in this left table, and values of x slightly bigger than 3, which are all of these x's in the second table. They should also be very close to 3. You wouldn't want to just pick, 5, 4, 2. You want to pick values that are really, really close to the number that you're interested in. And it's a good idea so that you have a nice, appropriate amount of numbers to justify your reason. I like to make tables that have at least 3 x values that are smaller than the number we're looking at, and 3 x values that are slightly bigger than the number you're looking at. That way you have enough sort of proof to justify your claim of what the limit is. So let's go ahead and figure out what these values are going to be. So I'm going to have to go back to my y equals, and I'm going to type in my function. Now make sure when you type in this g of x that you use parentheses around the numerator and around the denominator. It's very, very important that you do so, otherwise you're not going to be graphing the function that you think you are. So we need parentheses x squared minus 9, divided by parentheses this whole denominator x minus 3. Now I have it typed in. Let's go ahead and find these table values. So I'm just going to use my table feature. I'm going to change my table set to start at 2.1, and I'm going to go by tenths. So I'm going to change my change in table to 0.1, and I'm going to do second table. So what this tells me is that at 2.1 I get 5.1, and if I scroll down, at 2.9 we get 5.9, and I'm also seeing that at 3.1 this is 6.1. Now notice right at 3 we get an error. Why would we get an error on our calculator when x is 3? If you look at this function right here, notice what happens if you were to plug in 3 for x. In the denominator you would get 3 minus 3, which is 0, and we're never allowed to divide by 0. So what that means is that this function g of x is not defined at x equals to 3. It doesn't exist. So when we get to our graph later on, if you're not defined at a number, that means you're going to have a hole in your graph. So this graph of g, whatever it ends up looking like, is going to have a hole right at x equals to 3. Okay, let's finish filling out our table. So I'm going to change my table set here to be at 2.99. And I'm going to go to second table, and this would be 5.99. And if I change my table set to be at 2.999, then this is going to be 5.999. Now I presume that you can do this for the 3.01 and so on. I'm not going to waste your time watching me slowly do that on my computer. So at 3.01 you get 6.01, then 6.001, and 6.0001. So a nice pattern there. Okay, so what is this table now telling us? Well, as the x values get closer and closer to 3 from below, what are these y values wanting to do? Well, they're getting closer and closer to 6. And as these x values get closer and closer to 3 from above, these y values are also getting closer and closer to 6. So it seems like a logical conclusion that we can say that the limit as x approaches 3 of this function x squared minus 9 over x minus 3 is going to 6. So that limit is equal to 6. Okay? So that would be our numerical approach. Now let's do a graphical approach. So let's take a look at what the graph of this looks like. We already have it typed into our y equals, so if we go ahead and we hit graph, here's what we see. Now this might look a little strange because what you're looking at right here appears to be just a line. And let's figure out why that might be. Notice that if you have x squared minus 9 over x minus 3, you might notice in the numerator that x squared minus 9 is called a difference of squares, which means it factors. It factors into x minus 3 times x plus 3. And the fact that we have an x minus 3 on the top and the bottom means they end up canceling each other out, giving us x plus 3 right back again. So we end up seeing the graph of x plus 3. Are these really the same exact two graphs? Well, let's investigate it a little bit here. The graph of x squared minus 9 over x plus 3 will be the same as the graph of x plus 3, except for one little thing, and we mentioned that earlier. Remember the way that this function was defined. When you plug in 3, the function isn't defined at 3, which means that we're going to have a hole in our graph. So these two graphs, x squared minus 9 over x plus 3 and x plus 3, are exactly the same graph, except x squared minus 9 over x plus 3 is going to have a hole at x equals to 3. So let's graph x plus 3. That would be a line with a y-intercept at 3 and a slope of 1. So it's going to look something like this. Now I'm leaving a little gap here because when x is equal to 3, remember that is where your hole is going to go. So it looks just like a line, except we have this one little tiny hole left out, and you can't see that using your graphing calculator. It doesn't show it to you graphically, so you have to trust your mathematical instinct here that there is a hole in the graph because the function is defined as a fraction, which forces it to have a restriction in its domain. So if this is the graph of g, now let's take a look graphically as to what the limit is going to equal. So we want to look at the limit as we approach 3, which is down here. And we want to look at x's that are slightly bigger than 3 but getting closer to 3. So all these x's down here. What would those y values correspond to on the graph? Well, they would be all these y values coming down like that. So you have a car driving down the line just like this towards that hole. Now let's take a look at some x's slightly smaller than 3 from the left-hand side. So I would be wanting to look at these x's down here, which correspond to these y's up here. So as I get closer to 3 going this way, that means I'm driving up the curve this way. Do these two cars want to crash? Okay, do these cars want to crash? I say they do, yes. They want to crash into each other right where that hole is. Does it matter that there's a hole there? In the terms of limits, the answer is no. Holes do not affect the limit. It's only going to be what matters as we get close to 3, not what happens right at 3. So what you need to ask yourself is, do the cars want to crash? Yes. And at what height do they want to crash at? And since they want to crash right at this open circle, which happens to be at a height of 6, then that is what we get to say the limit is. It doesn't matter that there is a hole there, because limits only look at what happens near 3, not what happens right at 3. So that's an important distinction that's kind of confusing for students. But basically the idea is you can ignore a hole. It doesn't affect whether or not a limit is going to exist. Okay, let's try another example. Now this next example is called a piecewise function. It's defined using two different formulas. So we have h of x is equal to x plus 1 for all x's except for 1, and h of x is equal to 5 when x equals to 1. So let's think about the graph of h of x equals to x plus 1. What would that look like? Well, that's just a line with a y-intercept of 1 and a slope of 1. So it would look kind of like that. Now, this particular function h is not allowing us to use this line everywhere. We can use it everywhere except when x is equal to 1. And when x is 1, that would be this dot right here. So since we're not allowed to use that dot, what I have to do is take it away and put a little circle there, a little hole in the graph. I get to use all the other points, but I don't get to have that little hole. Now, what do we get to do when x is 1? Well, that's what this other piece tells us. When x is 1, we're supposed to be at 5. So when x is 1, I'm supposed to have a little dot right at 5. So this is what the graph of h of x looks like. It's just a line with a hole at 1 and a separate little dot sort of floating up above at a height of 5. So if we now have this graph, let's see if we can figure out what the limit of this graph is going to be as I approach 1. So here's 1. If I'm coming from the right side of 1, I'm looking at x's slightly bigger than 1. That would be these x's here, which correspond to these y's on the graph up here. So I'm looking at this car driving down towards that hole. Now let's look at the other side. If I'm approaching 1 from the left side, slightly smaller than 1, then I'm looking at all these x values driving up the curve towards that hole. So here's what you need to ask yourself. Do these two cars want to crash? Yes. Does it matter that there is a hole right where they want to crash? No. Does it matter that there's this extra little dot floating up above that hole? No. We don't care what happens right at 1. We only care what happens near 1. And near 1, those two cars want to crash. And at what height do they want to crash at? Where are their two arrow tips going to hit each other? They're going to hit right here at a height of 2. So we get to say that the limit is equal to 2. The hole and the dot do not affect the limit. And the reason why is because the limit only cares about what happens near 1, not what happens at x equals to 1. So it doesn't matter that there was this separate dot, which is the value. This is f of 1 right here. We don't care what f of 1 is. We just care what happens right near 1 on either side of it. So that's a tricky idea, but just remember that holes and these extra little floating dots don't matter. It's only going to be, do the cars crash and where do they want to crash? And if they crash, that's your limit. Okay, let's take a look at a couple of examples here that deal with some trigonometric functions. So now my function f of x is sine of x over x, and I want to find the limit of this function as I approach 0. So I have a table of values of x's that are positive but getting closer and closer to 0. So these would be coming from the right hand side, slightly bigger than 0. And then these x's are all negative, so they're to the left of 0, slightly smaller than 0 but still approaching 0. So we're going to pick a bunch of x's, a little bit bigger and a little bit smaller, find out what their y values are, and if these y values seem to be approaching the same value on both sides, then we'll have a limit. So let's go to our y equals and let's type in our function. Now make sure that you're in radian mode, not degree mode when you're doing this. Whenever you're in calculus, we always want to be in radian mode. So I'm going to type in sine of x divided by x And just to show you, my mode here is in radians, not degrees. And I'm going to go ahead and type in my table set, and I'm going to start it at 0.1. And I'm going to click on table. So at 0.1, I get 0.99833. If I arrow up, at negative 0.1, we get 0.9983 as well. And notice right at 0, we get that error message again, and that's because f of 0 does not exist, is undefined. Can't divide by 0. So that means this graph, whatever it looks like, must have a hole right at 0. Okay, let's change our table set to 0.01. And I'll change my table to 0.01 as well. So at 0.01, we're getting 0.99998, and at negative 0.01, we arrow up here, same thing. Okay. All right, let's try 0.001. And I'm going to change my table values to 0.001 as well. So at 0.001, I get 1. And negative 0.001 is also 1. All right, let me show you one more here. If I do 0.0001, we get 1. And you can see in the table that all of these are 1. So when I scroll up, you'll see that that is 1. And in the rest of the table, I'm going to save some time here, you get 1s for these as well. All right? So on this one, it seems pretty obvious what our limit is going to be. As we approach 0 from the right, get smaller and smaller values, but closer and closer to 0 from the positives, these y values are going to 1. And likewise, as we get closer to 0 through the negatives, these are also going to 1. So this graph is going to, or this function is going to have as its limit, as I approach 0, a value of 1. Okay? All right, let's take a look at another example with a trig function that has a graph. So I'm going to graph this next one. So let's clear this out. And I'm going to graph the function sine of 1 divided by x. Again, you want to be in radian mode, especially when you're graphing. So I'm going to go ahead and hit graph. And here's what I see. And we're trying to find the limit of this as we approach 0. So keep in mind, if you're looking at a limit as you approach 0, you should be looking at a graph or a table where the x values are really close to 0. And 0 is right here in the middle. So I really need to kind of zoom in on this graph right around the origin to get a better feel for what's happening. So you can do this lots of different ways. I'm just going to do a zoom box. And I'm going to arrow over and up. And see my little cursor there. And hit enter. And then I'm going to arrow down a little ways and to the right, and I'm basically just dragging a box over that origin so I can kind of zoom in there. And here's what we see. Now if you need to zoom in more, you certainly can, but the idea is that this graph has a lot of oscillations going on here. So I'm going to just give a rough sketch of what this graph is starting to kind of look like. It's looking like this. Okay, so we see something like this, and I want you to imagine what that means graphically about what this limit is going to be. As x gets closer and closer to 0, as I come in this way and this way, imagine what these cars are doing. They're going up and down and up and down and up and down, and on the other side up and down and up and down and up and down, up and down. Are they going to crash into each other? It's really hard to tell because they're going up and down so often and they're oscillating back and forth infinitely often that it's really hard to tell whether they're going to crash. And so what we say is, because as x approaches 0, since this function f of x oscillates between -1 and 1 infinitely often, the limit does not exist. And sometimes the way that we'll abbreviate that is we'll say that the limit as x approaches 0 of sine of 1 over x is dne, does not exist. So in order for a limit to exist, you need to be approaching a single number, single finite number. And in this particular example, we are bouncing back and forth between -1 and 1 infinitely often, so there's not a single number that we are approaching because we're bouncing back and forth between all those numbers between -1 and 1. So there's not a single limit, and that's why the limit does not exist. So that's one thing to look for when a limit doesn't exist, the fact that you might be oscillating so much that there's not a single limit value. Okay? All right, let's take a look at the next example. We're going to estimate the limit of ln of x over tangent pi x as x approaches 1 numerically. Now this one I didn't give you a table at all because I wanted you to kind of come up with one on your own. So if this problem was given to you and it tells you to find the limit numerically, that means to use tables. So you'd want to make 2 tables, and in these tables you want to be approaching 1 from above and from below. So think about 1 on a number line. Okay, if we're coming from above and we're coming from below, what kind of numbers would those be? So if we were coming from below, then we would be looking at something like 0.9, 0.99, 0.999, and so on. Okay, usually 3 or 4 values is sufficient. If we're coming from above, then we're slightly bigger than 1, but just a little tiny bit bigger. So maybe 1.1, 1.01, 1.001, and 1.001. So that's what you would want to do to create for yourself your own tables. So then you're going to go over to your y equals, and you're going to clear this out, and you're going to type in your function, ln of x divided by tangent of pi x, close the parentheses. And then we would go to table set, and I'm going to start at 0.9, and I'm going to go by 0.1. And I would get 0.32427. At 1.1, we get 0.29333. And again, we're seeing that error message right at 1, because if you were to plug in 1 in the denominator, you'd get tangent of pi times 1. Pi times 1 is pi, and tangent of pi is sine of pi over cosine of pi. And sine of pi is 0, cosine of pi is -1, so 0 over -1 simplifies to 0. That means you're dividing this whole fraction by 0. So that's why it does not exist. So then if we go and we change our table start to 0.99, we're going to get 0.31981. And if I go to 0.999, .31847, And you kind of get the idea. I'll just go ahead and tell you the rest of these. 0.31833. 1.01 is 0.31662. 1.001 is 0.31815. And 1.0001 is 0.31829. Okay? So as x approaches 1 from below, slightly smaller than 1, what do these y values look like they're approaching? Well, these first 3 digits here are starting to stay the same. Now, if this wasn't convincing enough to you, then you should add more values to your table and get even smaller values and keep making these x's get smaller and smaller until you are convinced. But to me, with enough digits here to match, I can fairly confidently say that this is going to be approaching about 0.318, and it's verified over here on the right side as well. So as x gets closer to 1 from above, these y's are also going to approximately 0.318. So we could say with some confidence that x goes to 1, the limit of ln of x over the tangent of pi x is approximately 0.318. Now, finding limits numerically is kind of tedious to do, but you're basically just letting the calculator help you find some table values. And finding limits graphically is also not too difficult to do as long as you can get a graph. However, there are some limitations to doing them graphically and numerically. And here's sort of a contrived example to show you that there could potentially be some pitfalls that you have to look out for. So again, this is a contrived example, not something you would run into every day, but imagine a function that had a graph that looked like this. Now, if you were being asked to find the limit of this function as x approaches 0, if you were going to do it numerically, like we just did that last example, chances are you would make a table, and we're looking as we approach 0, so we'd probably look at 0.01, 0.001, and we could even go as much as this guy right here, all those zeros, and we could find the corresponding y values. And for this y value, we know that it's 0.5. So these are really, really tiny. So as you get closer and closer to 0 from this direction, you'd probably, without hesitation, say that the limit must be equal to 0.5 because we are so close to 0 that this y value here has got to be pretty much what the limit is. And I would justify that. I would say that that looks like a pretty good proof to me because you are looking at such small values. So it would seem correct to say that the limit is 0.5. But in fact, that is not what the limit is. Because if you go even slightly smaller, imagine looking at this graph and imagine looking at x's slightly to the right of 0 and imagine driving along this curve. You would be driving up towards that dot on the right side. And if you picked some x values that were just slightly smaller than 0 on the left side, then that means you would be driving along this curve coming down like that. And where do those two cars want to crash? Right at this dot, which has a y value of 1. So in fact, the limit, according to the graph here, is actually 1. So what's the pitfall here? Well, the pitfall on this particular example is that you probably wouldn't have picked small enough x's to get the true limit. I mean, everyone in their right mind probably would say, oh, but this is definitely small enough, so we should be confident that our answer is 0.5. But if we had just picked one more 0 in there, then we would have been on this little stretch of the graph, and we would have indeed have gotten an even different y value, so we would have had a different limit. So if we did it numerically using a table, we probably wouldn't have picked small enough x's to get the right limit. If we were doing this graphically, we would also have issues. Because if we're doing this graphically, you probably wouldn't have zoomed in enough to see the whole graph and therefore get the right limit. So imagine you type in the formula for whatever this function happens to be. If you looked at this graph, you probably wouldn't see this little tiny line segment right here because you're not looking at a small enough window, because these are so tiny. Most people wouldn't think that they need to zoom in, 50 million times until they see that little tiny piece, because we're not expecting it to be there. We're expecting this graph to just do what's expected, and that is to connect together at a height of 0.5. So in this particular example, it's easy to get the wrong limit because you haven't either picked small enough x's or you haven't zoomed in enough on your graph to see the little piece that actually determines the limit. So you do have to be a little bit careful. All right, let's go on to another example here. This next one is pretty common. It's called the Heaviside function, and this is something you will see over and over again in a lot of your homework problems, variations of this particular function. And it is defined to be the absolute value of x over x. So what we want to do is come up with the graph of this. So to figure out this graph, it's actually a piecewise function because it depends on the value of x, whether x is positive or negative, to determine what value this is going to take on. So let's look at this in pieces. Let's look and see what happens if x is greater than 0. So for example, if I let x be 1, absolute value of 1 is 1, divided by 1 is going to give me 1 back again. If I plug in 2, absolute value of 2 is 2, over 2 also gives me 1. If I plug in 3, 3 over 3 is going to cancel out to a 1. So what we get is when x was 1, I got 1. When x was 2, I got 1. When x was 3, I got 1. In other words, when x is positive, we're going to get x back again, same sign, because it's already positive, so we don't even need those absolute values in there, divided by the same exact x, so it's going to give me 1 back again always, no matter what x is, as long as it's positive. So what does the graph of the constant function 1 look like? It's a horizontal line. So this is going to be a horizontal line going to the right for all of these positive x values. Okay? Now let's see what we get if x is negative. So what happens if x is less than 0? Well, if I plug in negative 1, the absolute value of negative 1 becomes positive 1, divided by negative 1 becomes negative 1. So when x is negative 1, I got negative 1 back. Now let's plug in negative 2. Absolute value of negative 2 becomes positive 2, divided by negative 2 reduces to negative 1. So I get negative 1 back again. If I plug in negative 3, absolute value of negative 3 becomes positive 3, divided by negative 3, so that reduces to negative 1 as well. So if x is negative, the top needs to become its opposite because you're already starting with a negative number inside of the absolute values. So to make it become positive, you do its opposite. So I'm going to write that as the opposite of x divided by the original x. Those cancel out, and that is why we're always getting negative 1 back again. So for all of these negative x's, I'm going to get negative 1 back. So we get another horizontal line. Now what happens right at 0? Well, if we plug in 0, we get 0 over 0, and you're not allowed to divide by 0, so this is undefined. So how do we show that on our graph? We don't want to have nice little solid dots right at these two endpoints because that would assume that it's including 0. So I want to leave 0 out, and I show that by having two open circles. So this is what the Heaviside function looks like. It's kind of like two big steps, one to the right and negative 1 to the left. So if this is what our graph looks like, let's talk about the limit as we approach 0. So I want to look at 0 coming from the right-hand side. So for values of x slightly bigger than 0. Since I'm on the right-hand side, those are positive x's. That means I'm on this part of the graph up here that's at a height of 1. Now if I go to the left of 0, and that means now I'm talking about negative x's, that means the y values I'm looking at are actually all these y values at negative 1. Is this car up here at a height of 1 going to crash with this car down here at a height of negative 1? No, because they're at different heights. So what do we say about this limit? Well, if they're not going to crash, then that would be a limit that does not exist. And usually we just write DNE for does not exist. So this would be another case where you would have a limit that doesn't exist, and what it looks like is kind of this jump in the graph where the two cars are not going to crash because they're kind of on different roads. Now in this particular example, we can talk about what are called right-hand limits and left-hand limits, or one-sided limits, and there's some special notation for this. The right-hand limit would be written this way. We would say, what is the limit as I approach 0, and then I'm going to put a little plus sign right in that upper right corner of the 0. So what is the right-hand limit of this graph? Well, if you're looking at a right-hand limit, that means you're only looking at values of x that are slightly bigger than, slightly to the right of 0. So that would be all of these points right here on our upper graph. And what are those y values of all of those points? They're all 1. So this is going to have a right-hand limit of 1. Now if we look at a left-hand limit, the notation for that is the limit as x approaches 0, and we put a little minus sign in that upper right corner. And that implies that you're only supposed to look at values of x that are slightly less than 0, which in this case would be negatives. So if I'm looking at these negative numbers as I get closer and closer to 0, that means I'm looking at all these x's down here. What are all those y values equal to? Well, they're all equal to negative 1. So we would say that this does have a right-hand limit, which is equal to 1, and it does have a left-hand limit, which is equal to negative 1. But the fact that the right-hand limit was different than the left-hand limit is exactly the reason why the limit from both sides is DNE. These two guys down here have to match in order for the two-sided limit to exist. Okay, and that's a theorem that we'll talk about in a little bit. Alright, so again, this notation, if you see the little plus sign above that A, that means you're only supposed to use x values that are slightly greater than A. And if you see the little minus sign, that means you use values of A that are slightly less than A. Okay, let's take a look at another example. P of x equals 1 over x cubed. So let's get a graph of this first. So I'm going to clear out my y equals and type in 1 over x cubed. Hopefully you already know what this looks like. It's just one of those reciprocal graphs. Oops, I forgot I'm in a weird window. Let me change this to a standard window. So I'm going to get these two branches. When x is 1, I get 1 back. So I know it goes through 1 comma 1. And when x is negative 1, negative 1 cubed stays negative. So this goes through 1, negative 1 as well. So we get those two sort of center points, and then we get this branch that goes this way, and this branch that goes this way. And we have a couple of asymptotes going on. As x gets really big, this fraction gets really small, which is why it's leveling off towards 0, and that is true going to the right and to the left. If x gets really small, then the fraction gets really big, so that's why it's shooting up here for positives and shooting down here for negatives. So that's kind of where the graph is coming from. Now let's take a look at our limit. So imagine that we are looking at the limit as I approach 0, and this is assuming 0 from both sides because I don't see that little plus or that minus up there. So let's find the limit from both sides. Well, here's 0. From the right side would be these x's here. Now, what y values do those correspond to? All these little tiny x's correspond to all these y's going up like this. Okay? So, on our graph, this car is shooting up, driving up, 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 up. Now, if we look at the other side, as I approach 0 from the left side, all these little x's down on the left side of 0 correspond to all these y values going down on my graph like this. So this car is driving down, 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 down. Do these two cars want to crash? Obviously not. One's going up, one's going down. So what we say is that the limit from both sides of 0 is d and e. Now we can be a little bit more descriptive here if we talk about the one-sided limit. So let's do that for a moment. Let's look at the right-hand limit as I approach 0 from the right-hand side. So put that little plus in there. So to figure out what this limit is, that means we're looking at as we approach just from x is slightly bigger than 0. So the right-hand side here, which corresponds to this black car driving up. Where is this black car driving towards? Well, it's going up, 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 up. And what is that called when you keep getting bigger and bigger and bigger in the positive direction? That's positive infinity. Okay, so we would say that the right-hand limit goes to positive infinity. What about the left-hand limit? So 0 with a little negative in there. Well, if we're on the left side of 0, then that means we're on all these y values here, and that car is going down, down, down. It's still getting bigger, but it's getting bigger in the negative direction. So this limit would be minus infinity. Now, is that actually a limit? Can a limit be infinity? Not really, because to be a limit, you have to be a finite number. You have to approach a single finite number, and obviously infinity or minus infinity is not finite. So technically, these are limits that do not exist. Both of these do not exist. But sometimes we write down plus infinity or minus infinity like I did here, just to be a little bit more descriptive about why the limit does not exist. So if I say that a limit is infinity, I know in my head that that means it doesn't exist, but I also know why it doesn't exist, and that's because the graph is shooting up towards infinity. So it's just a little bit more descriptive. Okay, let's try to formalize and summarize our idea of a limit. So the general idea of a limit is that suppose that a function f is defined near but not necessarily at x equals to a. So this allows for the possibility of f to maybe have a hole right at x equals a when we say that it's defined near it but not necessarily right at x equals to a. So this is allowing for possibly having holes or even asymptotes in your graph. So suppose we have such a function. To say that the limit as x approaches a of f of x equals to L means informally that f of x approaches L as x approaches a. So just as we would expect, f of x gets closer and closer to L as x gets closer and closer to a, or you could say that the function f of x is approximately the value L if x is approximately the value a. And that's true if the limit of the function is equal to L. Limits matter in calculus because there are often lots of functions in calculus that have gaps like holes and asymptotes in their domains. This often happens when you're trying to find a derivative. Most limits encountered in calculus are relatively simple and straightforward. You can solve them algebraically by just plugging in the limit value that you're looking at, this a value, or you can solve them graphically like we've been doing with our crashing cars, or numerically like we've been doing with our table of values. So most of the time we can solve them one of those three ways. Now our informal definition of a limit says that if f of x tends to a single number L, and this needs to be a finite number L, and again notice that word single, it has to approach one single number L as x approaches a, then the limit as x approaches a of f of x is equal to L. Here's the formal mathematical definition of a limit. It says that suppose that for every positive number epsilon, no matter how small, there is a positive number delta, so that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus a, which is less than delta. So this is probably very confusing to you, and we're going to talk about it quite a bit in just a few pages. But the idea here is really that given any really small epsilon, you can be within a distance of epsilon of this limit L, as long as you are within delta of a. So you can get as close to the limit as you want within any epsilon, as long as you are close enough to a, namely within delta of a. So what do these definitions of the limit sort of imply? Let's talk about a few comments that we have here. Number one, they say that you can estimate limits because the limit as x approaches a of f of x equals to L implies that f of x is approximately L if x is approximately a. So in other words, as long as you're getting close enough to a, you should be getting close enough to L. And that's why we're able to use our tables and our graphs near x equals to a to help us figure out what the limit is. So as long as we're using tables and graphs and picking our x's close to a, that will get us close to L. Okay? What about if we have a gap or a hole or an asymptote at a? What does that imply about our limit? It means no problem, because remember that the limit as we approach a only cares about what happens near a, not necessarily what happens right at a. So the limit may exist even if the function has a hole or is undefined right at a. So in other words, holes don't affect the limit. And usually this f of a value is undefined in the more interesting cases where you have graphs that have holes in them, asymptotes, and strange behavior going on. So in the case of limits, it doesn't matter what happens right at a, just what happens near a. And then finally, number 3 here, even if f of a is defined, there's no guarantee that the limit is actually equal to how the function is defined at a. And this would be that picture of having a graph that potentially has this limit right where this hole wants to be. However, the function is defined to be something else entirely right at that value. So up here, this little black dot would be our f of a, but this height right here would actually be our limit L. And they're not equal, obviously. Where the hole is, which is the limit, is not at the same place as where the dot is, which is up here. So the limit definition doesn't look at that little black dot, that little f of a. It only looks at what happens near a. So in this case, as we drive along our graph here from the left and from the right, as we get near that hole, where are we approaching? We're approaching this L. So this is really important, this statement right here. Okay, the limit doesn't look at what happens right at a, it only looks at x's near a. Okay? And then down here at the bottom, we just have a summary of a couple of definitions and a theorem that we've already talked about. So a right-hand limit would have this notation with the little plus sign right above the a, and that would say that you're looking at values of x that are to the right of a. So you should be picking x's that are slightly bigger than a, and that would give you your right-hand limit. If you see a little minus sign right there, then that means that you should be looking or picking x values that are slightly to the left of a, so slightly smaller than a, and that's called your left-hand limit. And then we have this theorem that says the two-sided limit right here, there's no plus and there's no minus, so the two-sided limit will exist if and only if both of the corresponding one-sided limits exist and are equal. So this should kind of make sense when we talk about some of the examples we've discussed already. If this right here is our right-hand limit, because we're approaching from slightly larger values of a, and this right here is our left-hand limit, first of all, we need each of those to be approaching a single finite limit value L. And in order for the two-sided limit to exist, not only do these two right-hand and left-hand limits have to exist, they better equal each other. Otherwise, we're going to see one of those jumps in our graph. So the only way all three of these can happen, or the only way the two-sided limit can happen, is if all three of these are equal to each other. Okay, now the next two examples that we're going to look at are very, very typical of the kinds of problems you'll see in your homework with this section. And it's going to require that you're very careful and you look at the graphs and you make sure that you're looking at both the left and the right sides, or whatever is appropriate for the question that's being asked. So here we have very complicated looking graphs. So let's start with the graph of f down here below. And what we're going to do is calculate a bunch of limits for this graph. So let's start by taking a look at the limit as I approach 0. Notice there's no plus or minus, so this is a two-sided limit. And we want that two-sided limit of 0. So what we want to do is find 0 on our graph, which is right here at the origin, and we want to approach from the right side and also from the left side. So if we look at the graph from the right side of 0, all these little x values here correspond to all these y values up here. And all these little negative x's over here to the left of 0 correspond to these y values up here. Are those two cars going to crash? Yes. And at what height are they going to crash at? Well, they're all at a height of 2. So this limit must be 2. Now let's take a look at the limit as I approach 2 from the right-hand side only. So here's 2. The right-hand side would be from this direction. And which part of this graph corresponds to those x values? That would be these x's coming up along here. So imagine your car driving up along here. Now we're only looking at the right-hand side. So where does this tip of the arrow of that little car want to stop at? Well, it wants to stop right at that hole. Does it matter that there's a hole there? No. Does it matter that there's this separate black dot defined down below at -1? No. The limits don't care about holes or these separate dots. It just matters where that tip of that arrow wants to end up at, which just so happens to be at a height of 1. So we would say that this limit is 1. Okay, now let's take a look at the limit as I approach -3. Again, this is a two-sided limit. So from the right side of -3, I would be coming in this way, which corresponds to these y values. And the left side of -3 would be over here, which corresponds to those y values. Do those two cars want to crash? Yes. Does it matter that there's a hole there or this separate black dot? No, it's just where those arrows are going to hit each other, and that is happening at a height of -1. Okay, how about the limit as I approach 2? So this is a two-sided limit. So from the right side of 2, we just talked about that. That's our car driving up towards that hole at a height of 1. And from the left side of 2, now we're on this curvy part of the graph, but still driving up towards that hole. It doesn't matter that there's a hole there. The fact that the two arrows want to point at the same hole and want to crash at that same point means there is a limit, and it's all happening at a height of 1. So this is equal to 1. Okay, how about the limit as we approach -1? Again, a two-sided limit. So from the right side of 1 are these x's, which correspond to these y's way up here. And on the left side of -1, we would be on these little x's, which correspond to this car driving up towards that hole. Do these two cars want to crash? No, we have one way up here at 2, and we have one over here that's approaching a height of 1. So there's a jump in our graph. So this is a limit that does not exist because the right-hand limit, which is 2, is different than the left-hand limit, which is 1. So we would say that this limit is DNE. It does not exist because of that jump in our graph. Okay, how about the limit as we approach -2 from the left side? So -2 from the left side would be these x's, which correspond to these y's. Now, where do these y's want to stop at? Where does the tip of that arrow want to end up at? We're not crashing in from the other side. This is a one-sided limit. So where's the tip of that arrow going to hit as we get closer and closer to -2? Well, it's hitting right here at that x-intercept, which means it's at a height of 0. So this limit would be 0. Okay, how about the limit as I approach 2 from the left-hand side? So here's 2 from the left-hand side would be along this curved part of the graph, and that means my car is driving up towards that hole. Doesn't matter that there's a hole there, the tip of that arrow wants to stop at a height of 1. So this limit would be 1. How about the limit as I approach 1 from the right side? So now we're coming in this direction. So we're driving down that curvy graph, and that means the tip of my arrow is heading down towards this hole right here, that intercept. Even though there's a hole there, it doesn't matter for the limit. That's happening at a height of 0. So the limit is going to be 0. Okay, now we want to look at the limit as I approach -4 from the right-hand side. So -4 from the right-hand side would be those x's, which correspond to these y's. So this car is driving down towards that black dot, which is at a height of -2. So the limit will be -2. Now we want the limit as we approach -1 from the right-hand side. So -1 from the right-hand side would be this direction for the x's, which correspond to these y's, and that arrow point is going right towards that black dot, which is at a height of 2. So this right-hand limit will equal to 2. Now we want the limit as we approach 4 from the left-hand side. So 4 from the left-hand side would be these x's, which correspond to these y's. So my car is driving down towards that open circle. That's okay that it's a hole, and that's at a height of -1. And finally, the limit as I approach -1 from the left side. So -1 from the left side would be these x's, which correspond to those y's driving up towards that hole. Doesn't matter that there's a hole there, it's just where that arrow point is ending up at, and that's at a height of 1. So this limit will be 1. Okay, let's try it with graph G. So here we have a different graph, and this time we want to find the limit as I approach -4 from the right-hand side. So here's -4. From the right-hand side would be like driving down this little curved graph towards that black dot. Where is that tip of that arrow wanting to end up? Right at that black dot, and that's at a height of 0. So this one-sided limit would be 0. Okay, how about the limit as I approach 0 from the left-hand side? So here's 0. From the left-hand side would be coming in this direction, which means my car would be driving down. Now notice I'm going to stop when I hit that y-axis because that's where 0 is. So where is this tip of the arrow hitting on that y-axis? Well, to me, it's not hitting at a nice integer, so I would probably approximate that to be about negative a half or negative 0.5. Doesn't hit right on the a nice number, so just estimate. Okay, how about the limit as x approaches negative 3? And this is a two-sided limit. So here's negative 3. From the right side, we would be these y's. From the left side, we would be these y's. So those two cars, are they going to crash? Yes. And they're crashing right at that little kink in the graph. And that kink is at a height of 1. So my limit is 1. Okay, how about the limit as x approaches 1? Again, another two-sided limit. So from the right side would be those x's, which are these y's. From the left side would be those x's, which are these y's. Do these two arrows want to crash? Yes. Does it matter that there's a hole there or this separate black dot? No, it doesn't. It's just where those two arrows are going to hit, and they're going to hit at a height of negative 2. So my limit is negative 2. Okay, how about the limit as x approaches negative 2? And this is a two-sided limit. So from the right side of negative 2, my car would be driving down to about here. And from the left side of negative 2, my car would be driving to about here. Obviously, those two cars are going to crash, and you just have to sort of eyeball what height that's at. And again, it's not right on a nice integer, so I'd probably estimate that this is at about a height of 1.5. So 1.5. Okay, how about the limit as we approach 2? Again, a two-sided limit. So from the right side, we're driving down to 2, and from the left side, we're driving up towards that number 2. Those two cars are definitely going to crash, and they're going to crash at a height of 0 because we're right on that x-axis. So the limit is 0. Okay, how about the limit as I approach negative 1 from the right-hand side? So coming in from this direction corresponds to these y's going up towards that hole. Doesn't matter that there's a hole there. We're only coming from the right side, so the tip of that arrow from the right side is ending up at that hole, which is at a height of 1. So this limit will be 1. How about the limit as I approach 3? From the right-hand side, I'm driving down towards that hole. From the left-hand side, I'm driving up towards that hole. That hole is at a height of 1. Doesn't matter that there's a hole there, so my limit is just 1. How about the limit as I approach negative 1? And again, it's a two-sided limit. So negative 1 from the right is driving up towards this hole. Negative 1 from the left is driving up towards that black dot. Are these two cars going to crash? No. From the left side, we're going to 2. From the right side, we're going to 1. So the left and the right side limits do not match. So if that happens, you have a jump in your graph, and you have a limit that is DNE. That's because we have that jump. Finally, the limit as x approaches 4 from the left-hand side. So 4 from the left-hand side, be coming in this way for your x's, which correspond to these y's driving up towards that black dot, and that black dot is at a height of 2. So my limit will be 2. Okay, let's explore the formal definition of the limit a little bit more. The definition says that let f be a function that is defined on an open interval containing a, except possibly at a itself. Then the limit as x approaches a of f of x is equal to L if, for any epsilon greater than 0, no matter how small, there exists a delta greater than 0, such that if x is between a minus delta and a plus delta, which is just another way of saying that the distance from x to a is less than delta, or the absolute value of x minus a is less than delta, then f of x is between L minus epsilon and L plus epsilon, which is just another way of saying that the distance between f of x and L is epsilon, or the absolute value of f of x minus L is less than epsilon. This is called the epsilon definition of the limit. And it's kind of confusing because it has all these deltas and epsilons and so forth going on. So the idea behind this is that you're going to pick any small epsilon so that you can get as close to this limit L as you want. And then you will have to be within delta of A. The size of delta is dependent on the size of epsilon, and usually we try to find this dependency relationship to help prove our limit definition. So here's what the picture is going to look like. You're going to have your function, and we're basically going to zoom in on this function on our calculator, and we're trying to get within epsilon of the actual limit. So here's my function. And as I approach A from the right and from the left, my cars are driving and they're approaching L. So obviously on this graph there is a limit right at L. Now what we're going to do is we want to get within epsilon of that L. So if we zoom in enough, we should be within epsilon above and epsilon below. If we want to be within epsilon above and below, what does that force us to have to be within the distance away from A? So how far to the right of A and how far to the left of A do I need to go so that I'll lie between these two horizontal lines? So what we're really forcing to happen is that this distance between f of x and L is within epsilon, and this distance between x and A is less than delta. So if we take a look at a very traditional type of example, what we would be given is that the limit as x approaches 1 of 4x minus 3 equals to 1, and we're trying to find out what delta will work so that epsilon is 0.01. So here we're given the epsilon and we're trying to find what delta that forces us to have so that we're within the right distance that we want to be from our limit. So if we draw a picture here, our function is just the line 4x minus 3. So we know what the graph of that looks like. And as I approach 1, this 1 right here is going to be our A value. Then as my cars drive on this graph, from the left and from the right, they're going to be reaching a height of 1. So the L, the limit, is this 1 over here. And this was our function. So what we're going to do on this picture is we want to kind of zoom in on this graph so that we're looking at a window that's a little bit above 1. In other words, L plus epsilon, or L plus 0.01, and a little bit below this limit, so L minus epsilon, or L minus 0.01. If we do that, if we zoom in so that we're within those two horizontal lines, what does that force us to have to be in terms of our x values? So how far to the right and how far to the left are we going to have to be so that my function is in between these two horizontal lines? So to the right would be our 1 plus delta, whatever that delta turns out to be, and to the left is our 1 minus delta. So we're trying to figure out what this delta is, and it's going to depend on this 0.01, this epsilon value. So the way you want to start these is to start with your normal definition of this limit. And this is what the epsilon delta definition says. It says that the absolute value of f of x minus L is less than epsilon whenever x minus A is less than delta. And we know what several of these pieces are. We know that f of x is 4x minus 3. We know that L is 1. We know that epsilon is 0.01. And we know that A, this number that we're approaching, is 1. So this is going to become x minus 1 less than delta. Now when we solve these problems, typically we're going to solve them sort of backwards. Whoops, sorry about that. My pen just went crazy there for a moment. So when we try to solve these, we're trying to solve them sort of backwards. we're going to work with this inequality right here and try to make this left-hand side look like this left-hand side over here. And that will force our choice of what delta needs to be. So let me show you what I mean. If I simplify inside the absolute values here, I'm going to get 4x minus 4 is less than 0.01. And if I notice that there's a 4 in common here that I can factor out, and it's positive, so when I pull it out of the absolute value, it just comes out front. This becomes 4 absolute value of x minus 1 less than 0.01. So if I divided both sides by 4, that would force x minus 1 to be less than 0.01 divided by 4, which is 0.0025. So that's how we're going to figure out what delta we need. We are going to choose this to be our delta. Now, if we make that choice, then kind of going in reverse here, that means that the original function, which was 4x minus 3, so this part right here, minus L, which was our 1, becomes 4x minus 4, which becomes 4 or absolute value of x minus 1. And we know now that the absolute value of x minus 1, we are going to let that be less than delta. And our delta here that we're choosing is this 0.0025. So this becomes less than 4 times 0.0025, and that is equal to 0.01. So we've just shown that the function minus L in absolute value will be less than 0.01 if we choose our delta to be 0.0025. Okay? All right, let's try another example, very similar. This time we want to use the epsilon delta definition of a limit to prove that the limit as x approaches 3 of 2x minus 5 is equal to 1. So again, we're going to kind of plug into this limit definition right here everything that we know. So we know f of x is this 2x minus 5, and we know L is this 1, and we want that to be less than epsilon. Now in this particular problem, they're not telling us a number for epsilon, so I'm going to leave it as epsilon, and we're going to try to figure out what the delta needs to be in terms of this generic variable epsilon. So whatever you choose epsilon to be, that will force us to use the right delta. So we want this relationship to be true whenever x minus a, and the a in this problem is the value that x is approaching, so that's this little 3 down here. We want this to be true whenever this absolute value is less than delta. So again, what we're going to do is kind of work with this side over here and try to make this absolute value right here turn into this one so that we can see what would be a good relationship between our delta and our epsilon. So we're going to start over here on the left. This reduces to the absolute value of 2x minus 6. I can pull out a 2, and that leaves me x minus 3 in absolute value. So if I divide by 2, that forces absolute value of x minus 3 to be less than epsilon over 2. So if we want x minus 3 in absolute value to be less than our delta, then we better let delta be epsilon over 2. So here's what we're going to say. We're going to choose delta to be epsilon over 2, so that if we do that, then our absolute value of our function minus L becomes 2x minus 5 minus that 1, which was 2x minus 6. Pulling out the 2 gives me that x minus 3, and we are letting x minus 3 be less than delta, and our delta here is this epsilon over 2. The 2's cancel, telling me that this piece right here, this f of x minus L in absolute value, is therefore going to always be less than epsilon if I choose my delta to be epsilon over 2. So we've just proven it. If we choose delta to be epsilon over 2, then f of x minus L will always be within epsilon. Alright, let's try another example. This one says, what if we mistakenly said that the limit as x approaches 1 of 2x plus 3 equals to 4? So here we're thinking that the limit is 4, but it really isn't. And what it would be, since this is just a nice straight line, as I approach 1, I should be getting whatever this line wants to be when x is 1. And if you were to plug in x equals to 1, 2 times 1 is 2, 2 plus 3 is 5. So the limit of this really should be 5, but we're saying that, well, what if it was 4? What would that say about our limit definition? So let's prove, using our limit definition, that this must be false. This must be a contradiction. So here's what we're going to prove, or this is what we're going to say. Let's choose an epsilon, and you can pick any epsilon that you want at all. Here I'm going to let epsilon just be a half. Can we find a delta that satisfies this epsilon delta definition? And the epsilon delta definition would say that x would need to be between 1 minus delta and 1 plus delta. And remember, this is the same as that absolute value notation. X minus a, and a here was 1, less than delta. So this is just another way of saying this absolute value statement right here. And this is just another way of saying that the function, whatever's here in the middle, this 2x plus 3, minus the limit, which is that 4, is less than a half. So these are just different ways of saying these absolute value statements. So in other words, if we let epsilon equal to a half, is it possible for this to be true? So what we're going to do is let, or assume, that it is true. Let's assume that if x minus 1 is less than delta, then this 2x plus 3 minus 4 becomes 2x minus 1. And if I factor out a 2, I can pull it out of the x, but what would I need to have left over here to make this equivalent, so that if I were to redistribute the 2, I would get back 1? This would need to be a half, so that 2 times x would be 2x, and 2 times a half would give me back that 1. So all I did was pull out a 2. And what we know about our epsilon delta definition is that this f of x minus L in absolute value is supposed to be less than our epsilon. So what that would say is, since we're letting our epsilon be a half, let's go ahead and divide both sides by 2 here, then that forces x minus a half in absolute value to be less than 1/2 divided by 2, which is the same as a quarter. Now, is that legitimate for this particular problem? Think about what this means. What is x minus a half in absolute value less than 1/4? And if you took intermediate algebra and you talked about absolute value inequalities, that's exactly what we're going to think about here. We're going to undo this absolute value and rewrite it in one of these kinds of statements. And the way we do that is we take whatever we see right here, x minus a half, and we have to squeeze it in between 1/4 and its opposite. So that's what this statement really means. Absolute value of x minus a half less than 1/4 means that x minus a half must be between negative 1/4 and positive 1/4. Now let's solve this for x. If we add a half to both sides, 1/2 minus 1/4 is 1/4, and 1/2 plus 1/4 is 3/4. So what this is saying is, if f of x minus L is less than epsilon equal to a half, that requires that x is between 1/4 and 3/4. Is that legitimate? Is that allowed? Think about what our epsilon delta definition says about x. What are we supposed to be looking at for x? X is supposed to be close to this limit value that we're approaching, which is 1. Is 1 between 1/4 and 3/4? No, this does not include x equals to 1, which is what we're trying to approach. So that can't possibly work for us, and that's how we get our contradiction. So no delta will exist if epsilon is equal to 1/2. And this limit definition has to work for every epsilon that you pick. So if we can show that there's no delta that works if we pick epsilon to be 1/2, then that automatically means that the limit definition, or the original definition of our limit, what we thought it was equal to, in this case 4, must have been wrong. Okay, so if there's even one value of epsilon where it doesn't work, then your limit is incorrect. Okay, let's try another example. And there's more examples like these in your textbook. They do take some getting used to, so if you need to see more examples, remember to look in your book. This next one says, use the epsilon delta definition of a limit to prove that the limit of x squared as x approaches 3 is equal to 9. So here's what we're going to do on this one. Same idea as before. We're going to use our limit definition right here, and we're going to plug in everything that we know. So our f of x in this problem is that x squared. Our limit L is this 9 right here, and we want that to be less than epsilon. And we're not given an epsilon here, so we're going to leave it as epsilon, and whatever delta we come up with will be in terms of epsilon. So in one of the previous examples that we did, we found that delta should be epsilon over 2, for example. So you'll kind of come up with a formula for delta that involves epsilon. So we need this to be true whenever x minus a, and a here is 3, is less than delta. So remember, what we're trying to do is make this absolute value over here have the absolute value of x minus 3 in it, so that we can get a relationship between this epsilon and this delta. So on this one, what we're going to do is notice that x squared minus 9 factors. It factors into x minus 3 and x plus 3. So think about what would happen on this interval. We are approaching 3. So what would be a reasonable range of x values to look at if we're approaching 3? Obviously you want to try to get as close to 3 as you can. So in a very worst case scenario, what you want to notice is that if x is in, this little e right here means an element of the interval 2 to 4. So if x is any number between 2 and 4, what can you tell me about the absolute value of x plus 3? How big could this possibly get? Well, if x was 2, this would be 5. If x was 4, this would be 7. And anything in between would have to be between that 5 and that 7. So the largest that this linear function here would take on is going to have to be 7. So we're going to make a bound here. We're going to say that the absolute value of x plus 3 cannot be any bigger than 7 as long as we pick x's between 2 and 4. Now, what's the delta that we're really talking about if we choose x's between 2 and 4, by the way? Well, remember, 3 is in the middle here. So how far to the right of 3 do we go, and how far to the left of 3 do we go? We go 1 up and we go down, 1 down to get 2 to 4. So if we choose x to be between 2 and 4, this means we're really choosing our delta to be 1. So if delta is 1, that forces a bound on this x plus 3. So if the absolute value of x minus 3 is less than delta, then the absolute value of x squared minus 9, which is absolute value of x minus 3 times absolute value of x plus 3, becomes less than, this is our less than delta, and this is our less than that bound 7. So if we multiply those two together, then this becomes 7 delta. So what should we choose our epsilon to be? What should we choose our delta to be so that this is less than epsilon? We need our delta to be either epsilon over 7, so we're going to choose delta to either be epsilon over 7, or it could have been that 1 that we chose up here to get our bound. Typically though, your epsilon is probably going to be very, very small, so epsilon over 7 would be the smaller of the two. So we're going to choose whichever one is the minimum of these two possibilities. And usually epsilon is small, so epsilon over 7 would be the smaller value. But if for some reason you chose a fairly large epsilon, then 1 might actually be the smaller value. So if we choose our delta to either be epsilon over 7 or 1, then our epsilon delta definition will be maintained. Okay, in our next example here, we're going to use our calculator. This one says, given the limit of the cube root of x is equal to 2 as x approaches 8, and let epsilon equal to 0.01, find the maximum value of delta accurate to 6 decimal places. Now, one of the reasons why we're going to be using our calculator on this is because if we attempted to do our epsilon delta definition and do that f of x minus L less than epsilon, in this problem, f of x is cube root of x and L is 2. And it's very hard to manipulate this like we've been doing in the last few examples, because this doesn't really factor into anything nice, and it's certainly not going to compare to the x minus 8 less than delta that we're going to try and want to compare it to. So when your function is something difficult like cube root of x, that's when you're going to pull out your calculator and use it to help you figure out what delta should be. And usually you can do that up to a significant number of decimal places, and this one is telling us to go up to 6 decimal places. Okay, so if your function is tricky, like cube root of x, then that's when you do it on your calculator instead of trying to do it algebraically using some factoring ideas. Okay, so here's what we're going to do to help us out on our calculator. We are going to try and construct this window in our graphing calculator. We want this to be what we see when we hit graph. Now, in order for that to happen, we are going to need to choose our y1, y2, and y3 very carefully, and we're also going to need to choose our x-mins, maxes, y-mins, and maxes very carefully as well. So look at what this window is supposed to be showing us. We've obviously got our function going on here, and we want to zoom in enough on this graph so that we can see on our window being within epsilon of this limit value L. So we want to be up by epsilon and down by epsilon between these two horizontal lines. Now, to be able to see those horizontal lines in our window, we're going to give our window a little bit of buffer space. So I'm going to actually set my y max to be L plus 2 epsilon and my y min to be L minus 2 epsilon, so that I have room to see these two horizontal lines. So we're going to let our y min be L minus 2 epsilon, our y max is going to be L plus 2 epsilon, and we're going to let our y scale be that epsilon. For our y's, I'm going to let y1 be the function itself, And then y2 is going to be this horizontal line, which is just the height L plus epsilon. And I'm going to let y3 be L minus epsilon. Then for the x's, we know that we're approaching our A, and in this case that's this number 8. So I want to center my window at that A value, and I'm going to go one less than it to the left and one bigger than it to the right. So my x min is going to be A minus 1, and my x max is going to be A plus 1, and my x scale is going to be 1. So by making these choices right here, you can make your window show up really, really nicely. And then what we're going to do once we get our graph to be set up really nice is we're going to figure out what our delta needs to be so that we're within these two horizontal lines. How far to the right should I go? How far to the left should I go? And once I find that delta 1 and that delta 2, because it may not be symmetric, delta 1 may be smaller than delta 2. And what we're going to do once we find those two deltas is make sure that we pick the smaller one. And that will ensure that if we go delta 1 to the left and delta 1 to the right, if that's the smaller value, will definitely be between L minus epsilon and L plus epsilon. So again, it's kind of tricky because of all the variables and letters going on, but let's see if we can figure this out. First thing we're going to do is let our y1 be our function, which in this problem is cube root of x. And then to get these two horizontal lines going across, we're going to let y2 be our limit, which is this 2, plus our epsilon, which is this 0.01. So I want to be just a little bit above my limit value. And then in y3, I want to be just a little bit below my limit value. So 2 minus 0.01. Now to be able to see those horizontal lines, I'm going to let my y min be this limit value 2 minus 2 epsilons, so 2 times 0.01, and I'm going to let my y max be 2 plus 2 epsilons, so 2 times 0.01, and I'm going to let my y scale be epsilon itself, so 0.01. Then for the x's should be centered around this limit that we're approaching. We're approaching 8. So I want to go 1 to the left of that, so 8 minus 1 would be 7. And I want to go 1 to the right of that, so 8 plus 1 would be 9. And I'm going to let my y scale just be 1. So let's go ahead and type all of that into our calculator. So in my y equals, clear out what we have in there right now, and we're going to type in cube root of x. You can do that several different ways. I'm just going to do x to the 1/3 power, because that's what a cube root is. There's also a built-in cube root button under your math key, so you could use that as well. So there's my y1. Oops, let me close my parentheses on that just to be safe. In y2, we want our horizontal line 2 plus 0.01, and you could just type in 2.01 if you want. And in y3, I want my other horizontal line 2 minus 0.01. And then we're going to go to our window, and we're going to type in for our x's. Remember, our x should be centered around that 8. So I want to go 1 to the left of it, which would be 7, and 1 to the right of it, which would be 9, and an x scale of 1. So that's good to go. And then to be able to see my limits and my horizontal lines, I want to make sure that my window is centered around that limit value. So I'm going to let my y min be the limit, which was 2, minus 2 of those epsilons. So 2 parentheses 0.01. And it'll convert that to a decimal when I go down here. And then in y max, I'm going to do 2 plus 2 epsilons. It's just so that I have good space to see a little bit above and a little bit below my limits. And then finally I'm going to change that y scale to be epsilon, so 0.01. And now I'm going to hit graph, and we should get a picture that looks just like ours over here. There's that top horizontal line and there's that bottom one. Okay, so now what we're trying to do is we know that we want to be within these two horizontal lines. So what does that force us to have to be for our x's? So what we're going to do next is find these two little intersection points. The intersection point between the function and the top line, and the intersection point between the function and the bottom line. And to find an intersection, you're going to go to this calc command. So I'm going to do second trace to hit calc, and intersect is number 5. And let's do the upper intersection point first, so I'll just arrow up, get your cursor over top of it as close as you can, and just hit enter 3 times. And then we want to write down that intersection point. So the upper intersection point in my little picture here is 8.120601, and you don't need to worry about the y value because we know that that's at that horizontal line. It's really the x value that we're interested in. Now let's go and find this lower intersection point and find out what its coordinates are going to be. And remember, the limit L is right here in the middle. Okay, so I'm going to go back to my calculator, and I'm going to do second calc. I'm going to do intersect, and this time I'm going to arrow to the left to get to that lower point, and just hit enter 3 times. Oops, I think I must have missed it. Let me go back and try that again. Number 5, because I got the same point I had before, so let me make sure I'm lined up pretty good here. Let's go back one more. So enter. Oh, that was the problem. I forgot to switch curves. I don't want to be on the, I don't want to hit enter 3 times. I need to switch. There we go. My second curve should be the bottom line. And then enter again. So there we go. Now notice that my cursor is flashing down here. So I did find that lower point, and that has coordinates 7.880599. And you want to keep all those decimal points for accuracy. So we're really just interested in that x coordinate. All right, now that we have those 2 points, we're going to use those to help us figure out our delta 1 and our delta 2. And once we know what delta 1 and delta 2 are, we're going to take the smaller of those 2 deltas, and that will be the delta that will ensure that we are within epsilon of our limit. So let's go ahead and see if we can figure out what our delta 1 is going to be. So delta 1 is this horizontal distance from our center point, which we know is this limit value 8, and this intersection point over here, which was this 7.880599. So how do I find the distance between those 2 points? We just subtract. And I'm going to take the 8 minus the 7.880599, and that tells me that that horizontal distance, delta 1, is going to be 0.119401. And you can use your calculator for that. Now let's find delta 2 doing exactly the same thing. So delta 2 is the distance from 8 over to this second intersection point. So this is delta 2, this was delta 1. So if this is 8, and this is at 8.120601, we're just going to subtract. Do the bigger point, the one on the right, minus the smaller point, the 8. And when you subtract those on your calculator, you're just going to get 0.120601. Now, which of those two deltas is smaller? This one. So the delta that we want to pick is the smaller of the two. You always want to take the smaller one, because if you were to choose the bigger one, then on the left side over here, you wouldn't be far enough in to be within L minus epsilon on that left side. So always take the smaller of the two deltas. So this is the delta that we need to ensure that my cube root of x is within 0.01 of 2. Okay, let's try one last example. Assume that the limit as x approaches 0 of f of x exists for the following. For any epsilon greater than 0, discuss why it is impossible to find a value for delta such that if x minus a is between 0 and delta, then f of x minus L is less than epsilon, hence contradicting your assumption. Use a rough sketch to support your argument. So again, the idea here is that we're going to try to disprove this proposed limit. This is kind of like that other one that we did that was a contradiction. So here we're proposing that the limit as I approach 0 of 1 over x squared is equal to 0. And we're going to see why that is not possible. And the way we're going to show that it is not possible is we're just going to pick any epsilon that we want. You get to pick whatever you want for epsilon. And we're going to show that for that choice of epsilon, it is impossible to find a delta that works. Because based on this limit definition, you should be able to find a delta for every epsilon. So if we can show that it doesn't work for one particular choice, then this must not be a true limit. Okay, so that's kind of our idea. So the first thing we're going to do is we are going to assume that the limit is true, that the limit exists, and we're going to pick epsilon to be whatever you want. And I'm just going to pick 0.1, something relatively small. And if we pick this particular epsilon, then we should be able to find a delta that works. And when I mean that it should work, it means that that relationship, that f of x minus L less than epsilon is true whenever x minus a is less than delta. And in our particular problem, the function is this 1 over x squared. The limit that we're proposing here is 0. So that means 1 over x squared in absolute value is supposed to be less than epsilon whenever x minus a, and a in this problem is this 0 that we're approaching. And we don't even need that 0 in there since x minus 0 is still x. So this is what we're trying to show. Okay, that 1 over x squared is less than epsilon whenever x is less than delta in absolute value, and we're going to do this for our particular epsilon of 0.1. So we're going to use our calculator for this because it is very difficult to try and algebraically turn 1 over x squared into just an x to get that relationship between epsilon and delta. This isn't one that we can do algebraically because we have a more complicated function that we're working with. So that's when you use your calculator to help you out. And when you're going to do it on your calculator, you're going to set it up exactly the way we did on this last problem. All these things in black right here are always going to be true. You're going to use these every single time. So on our calculator, we're going to let y1 be our function, y2 be L plus epsilon, and y3 be L minus epsilon. So let's figure out what that would be for this problem. We're going to let y1 be our function, which was this 1 over x squared. We're going to let y2 be L plus our epsilon, and our L, our limit, was 0, and epsilon that we're using is 0.1, so this is just going to be 0.1, and y3 is going to be the limit minus epsilon, so that would be 0 minus 0.1 or negative 0.1. We are going to let our y min, so that we have a little room here to see these horizontal lines, we're going to let our y min be the L minus 2 epsilon, so the limit is 0, and 2 epsilons would be 2 times 0.1, so this is going to be negative 0.2. We're going to let our y max be L plus 2 epsilon, so that's going to be 0 plus 2 times 0.1, or a positive 0.2. And we're going to let our y scale be epsilon, which is that 0.1. Then for our x's, remember that we're looking at this as x approaches 0. So we want to center our window around 0. So we want to go 1 to the left of 0, so negative 1. Whoops, there's that crazy pen again. And then we want to go 1 to the right of 0, so 0 plus 1, which would be 1. And our x scale is just going to be 1. So let's type all of that into our calculator and see what picture we come up with. So in y1, we're going to type in 1 divided by x squared. In y2, we had 0.1. That was just our L plus epsilon, so 0 plus 0.1. And in y3, we want L minus epsilon, so 0 minus 0.1 is negative 0.1. Then for our window dimensions, for x, we were centering this around 0, so I'm going to go 1 to the left, so negative 1 up to positive 1 with a scale of 1. And then for the y's, to be able to see our horizontal lines, we would go L minus 2 times epsilon and L plus 2 times epsilon. So that was negative 0.2 up to positive 0.2. And our y scale was epsilon, which was 0.1. And we're going to hit graph. And remember, we're trying to see a picture that looks like what we had up here. We should see our graph going through and hitting these two horizontal lines so that we can find out what our delta is. But if you look at this picture, I see two horizontal lines, but I do not see my function intersecting it anywhere. And why might that happen? Okay, so let's draw what we see over here. If you're doing this on a test or homework, it's always a good idea to replicate a picture of what your calculator is showing you, since I won't be able to see your calculator. So draw a picture of it. Here's that horizontal line at a height of 0.1. Here's that horizontal line at a height of negative 0.1. And we would like to be able to see our function diagonally cutting through this so that we can find our two horizontal points. How come we're not seeing that? Well, let's just for a moment undo all of our nice window and let's do a little zooming out. That's what the graph of 1 over x squared looks like. And if you zoom out just a little bit, what you see is that it does not intersect. You can see over here on the left that the graph is intersecting that upper horizontal line. It's never intersecting the bottom horizontal line at all, because this graph never becomes negative. But the fact that it is hitting is bad because it's not hitting until way over here. Okay? And when we look at a limit, should be looking close to 0. So when we get close to 0, this graph is not intersecting our lines at all. It's lying way up here. So is it possible to find a delta so that this graph will be within 0.1 of 0? No, the graph doesn't get close enough to 0 within that distance. If we try to find this delta, it doesn't work. Okay, so let me summarize that. So since the graph does not intersect our two horizontal lines, which are at plus and minus 0.1, there is no delta that will make our function, which was 1 over x squared, be less than that particular choice of epsilon, which was 0.1. So by choosing this particular epsilon, we were not able to find a delta that would make the graph be low enough to hit these two horizontal lines. So this shows that the limit that we were assuming from the very beginning of it being 0 must be false, because we get a contradiction to our limit definition. Alright, so for these proofs by contradiction, the idea is to choose any epsilon you want, usually it's something relatively small, and then proceed through the limit definition, either algebraically if you can, or using your calculator if the function is too difficult to work with. And what you're trying to show is that by that choice of epsilon, it's impossible to find an accurate delta that will either exist at all or lie within the right range of values. And if you can't find that delta, then that shows that your original assumption of the limit must have been false. These are tricky problems and they take some practice. So you may need to re-watch this video lecture or read through your textbook to get some more ideas. Alright, that concludes our long lecture on finding limits graphically and numerically. Good luck.